Today, we're diving into the fascinating world of non-Newtonian fluids flowing through microchannels. We'll explore shear thinning behavior, viscoelastic effects, and how these complex rheologies fundamentally change droplet formation and particle migration. Let's start with the basics. What exactly makes a fluid non-Newtonian? In a Newtonian fluid like water or glycerol, the viscosity remains constant regardless of how fast you shear it. The relationship between shear stress and shear rate is linear. We can write this as tau equals mu times gamma dot, where tau is shear stress, mu is the constant viscosity, and gamma dot is the shear rate. But in non-Newtonian fluids, this relationship breaks down. The apparent viscosity depends on the shear rate it's. Here's the key difference. For Newtonian fluids, viscosity is flat. For shear thinning fluids, viscosity decreases as shear rate increases. This is sometimes called pseudoplastic behavior. Let me give you some everyday examples you can relate to. Blood is shear thinning. At low shear rates, red blood cells aggregate and increase viscosity. At high shear rates, they align with flow and viscosity drops dramatically, sometimes by a factor of 10. Polymer solutions like polyethylene oxide in water show both shear thinning and viscoelasticity. The long polymer chains can store and release elastic energy. Ketchup is the classic example. It won't pour when you tip the bottle gently, but when you shake it vigorously, it flows easily. You're increasing the shear rate and reducing its viscosity. Now let's get quantitative. The most common way to describe shear thinning is the power law model. The apparent viscosity is mu of gamma dot equals K times gamma dot to the power of n minus 1. Here, K is the consistency index and n is the flow behavior index. When n is less than 1, we have shear thinning. The smaller n is, the more pronounced the effect. When n equals 1, this reduces to Newtonian behavior with mu equals K. When n is greater than 1, we get shear thickening or dilatant behavior, like cornstarch suspensions. Let's do a back-of-the-envelope calculation for blood flowing through a microchannel. For blood, typical values are K equals 0.017 Pascal seconds to the n, and n equals 0.708. In a circular channel, the wall shear rate is approximately gamma dot equals 4q over pi r cubed, where q is flow rate and r is radius. Let's say we have a 50 micrometer radius channel with a flow rate of 0.1 microliters per second. The shear rate works out to about 1,000 per second. At this shear rate, the viscosity is 0.017 times 1,000 to the negative 0.292, which gives about 3.4 millipascal seconds. That's about 3 times water viscosity. But here's the key point. At low shear rates in smaller vessels or stagnant regions, blood viscosity can be 10 times higher. This drastically affects flow patterns. Now let's talk about viscoelasticity. This is where things get really interesting. Viscoelastic fluids exhibit both viscous dissipation like a liquid and elastic energy storage like a solid. They have memory. The key parameter is the relaxation time, lambda. This is the timescale over which the fluid forgets its deformation history. We quantify this with the Deborah number, dE equals lambda over tau flow, where tau flow is the characteristic flow time. When dE is much less than 1, the fluid has time to relax and behaves mostly like a viscous liquid. When dE is much greater than 1, deformations happen faster than relaxation, and the fluid behaves elastically like a solid. You might ask, why do these rheological effects matter so much in microchannels? Great question. Let me explain. First, in microchannels with dimensions of 10 to 100 micrometers, shear rates can reach thousands to tens of thousands per second. This is where non-Newtonian effects become dominant. Second, the surface-to-volume ratio is enormous. Wall effects dominate over bulk effects. The fluid near the wall experiences maximum shear. Third, while the Reynolds number is typically very small, meaning no turbulence, the Weissenberg number can be large for viscoelastic fluids, leading to elastic instabilities. The Weissenberg number is Wi equals lambda times gamma dot. It compares elastic forces to viscous forces. Now let's see how these rheological properties change droplet formation. This is crucial for microfluidic applications. In typical microfluidic devices, droplets form at T-junctions or flow-focusing geometries. A dispersed phase breaks up into droplets in a continuous phase. Here's a T-junction. The dispersed phase flows down, the continuous phase flows from the left, and droplets pinch off and flow to the right. For Newtonian fluids, the droplet size is primarily controlled by the capillary number, which is the ratio of viscous to surface tension forces. Capillary number is Ca equals mu u over sigma, where mu is viscosity, u is velocity, and sigma is interfacial tension. When the continuous phase is shear thinning, something interesting happens. Near the forming droplet, shear rates are high, so viscosity drops. This reduces the viscous stress and allows for smaller, more uniform droplets. With viscoelastic continuous phases, you get thread formation. The elastic stresses resist breakup, creating long threads that eventually break into satellite droplets. This is generally undesirable for monodisperse emulsions. When the dispersed phase is viscoelastic, elastic stresses inside the forming droplet resist deformation. Breakup is delayed, and you typically get larger droplets with broader size distributions. Let me give you a concrete example with DNA solutions, which are highly viscoelastic. Lambda DNA in buffer has a relaxation time of about 0.01 to 0.1 seconds, depending on concentration. At a shear rate of 1,000 per second, the Weissenberg number is 10 to 100. This is highly elastic flow. Experimentally, you observe long threads and beads on a string structures during droplet formation. The DNA chains stretch and don't want to break. To control this, you can add surfactants to reduce interfacial tension, or use hydrodynamic focusing with the sheath flow to apply more precise control over the breakup location. Now let's shift gears and talk about particle migration. This is equally fascinating and practically important. In Newtonian fluids at finite Reynolds numbers, particles migrate toward an equilibrium position at about 0.6 times the channel radius from the center line. This is the famous Segre-Silberberg effect. But what happens in non-Newtonian fluids? Does migration still occur? The answer is yes, but the mechanisms are completely different. In shear thinning fluids, even at zero Reynolds number, particles migrate due to shear gradients. The viscosity varies across the channel, and this creates an effective force on particles. The mechanism is subtle. Particles preferentially move toward regions of lower viscosity, which are typically the high shear regions near walls. This is opposite to Newtonian inertial migration. Particles enter uniformly at the inlet, but as they flow through a shear thinning fluid, they migrate toward the walls where shear rates and velocities are higher, but viscosity is lower. In viscoelastic fluids, there's another mechanism called elastic migration. Particles migrate due to normal stress differences in the fluid. The first normal stress difference is N1 equals tau 11 minus tau 22. This creates a lateral force on particles. The amazing result is that particles migrate toward the channel centerline. You get single-file particle trains along the center of the channel. This is called viscoelastic focusing. Let's estimate how fast particles migrate in a viscoelastic fluid. The migration velocity scales as u mig is proportional to a squared lambda gamma dot squared over eta, where a is particle radius, lambda is relaxation time, gamma dot is shear rate, and eta is viscosity. Let's use a 5 micrometer particle, relaxation time of 0.01 seconds, and shear rate of 1,000 per second. Plugging in numbers, we get u mig is about 5 times 10 to the negative 6 squared times 0.01 times 10 to the 6th over 0.001. This works out to about 0.25 millimeters per second. That's pretty fast for a particle in a microchannel. For a 1 centimeter long channel, this means particles would focus within about 40 seconds of residence time, very practical for lab-on-a-chip devices. Now let me tell you why all this matters for applications. These phenomena enable powerful techniques for cell separation. Using viscoelastic fluids, you can sort cells by size without any labels. Larger cells experience stronger elastic forces and focus more tightly to the centerline. A key application is isolating rare circulating tumor cells from blood. Tumor cells are typically larger than blood cells, so they focus to a different streamline and can be separated. The shear thinning properties of polymer solutions are actually beneficial here. They reduce the effective shear stress on cells, minimizing damage during high-throughput processing. Now let's put it all together and see how shear thinning and viscoelasticity combine. Here's the important point. Most biological fluids and polymer solutions show both shear thinning and viscoelasticity simultaneously. You can't just consider one in isolation. There's a competition between viscous forces, which tend to spread particles, and elastic forces, which tend to focus them. The balance depends on the Weissenberg number and the degree of shear thinning. We can define an elasticity number. EL equals Wi over Re. This tells us whether elastic or inertial effects dominate. In typical microfluidic applications, EL is much greater than 1, so elastic effects dominate over inertia. This is the regime where viscoelastic focusing works best. If you're designing a microfluidic device for non-Newtonian fluids, what should you consider? First, geometry matters enormously. Curved channels induce Dean flows that interact with elastic effects. Straight channels are simpler, but may be slower for focusing. Second, aspect ratio is crucial. High aspect ratio channels with height much less than width enhance elastic focusing by confining the flow. Third, you need to tune the flow rate carefully. Too low and elastic effects are weak. Too high, and you might get unstable flow or even elastic turbulence. Fourth, polymer choice matters. Polyethylene oxide, polyvinyl pyrrolidone, and hyaluronic acid are common choices with different relaxation times and biocompatibility. Let me briefly mention an advanced topic, elastic instabilities. When Weissenberg number gets very high, something dramatic can happen. Above a critical Weissenberg number, the flow transitions from steady to unstable and eventually chaotic. This is called elastic turbulence. The remarkable thing is, this happens with zero inertia. It's a purely elastic phenomenon driven by the stretching and relaxation of polymer chains. The critical Weissenberg number is typically around 5 to 10 for most geometries. Beyond this, you see time-dependent fluctuations. Interestingly, this is not always bad. Elastic instabilities can be exploited for enhanced mixing in microchannels, where regular turbulence is impossible. How do we actually measure these effects experimentally? Let me give you some practical techniques. Particle tracking velocimetry, or micro-PIV, lets you track individual particles and measure their lateral positions and velocities over time. High-speed imaging at thousands of frames per second captures the detailed dynamics of droplet breakup and thread formation. Measuring pressure drop across channels allows you to infer the apparent viscosity under actual flow conditions. Offline rheometry with rotational or oscillatory shear gives you the fundamental material properties, viscosity curves, relaxation times, and normal stress differences. Simulating these flows numerically is extremely challenging. Let me explain why. You need to solve the Navier-Stokes equations coupled with complex constitutive models like GSCS, Oldroyd B, or FENEP that describe the polymer stress. There's a notorious high Weissenberg number problem where simulations become unstable at realistic WI values. This remains an active area of research. When you add multi-phase flows with moving interfaces for droplet formation, the complexity explodes. You need sophisticated interface tracking methods. Let me summarize the key points we've covered today. Shear thinning means viscosity decreases with increasing shear rate. This is dominant in blood, mucus, and many polymer solutions. Viscoelasticity means the fluid has memory and can store elastic energy. The relaxation time lambda characterizes this. These rheological properties fundamentally change droplet formation, affecting breakup location, droplet size, and uniformity. Particle migration in viscoelastic fluids is driven by elastic normal stresses, enabling powerful label-free separation techniques. The applications range from cell sorting and diagnostics to controlled drug delivery and material synthesis. Looking forward, this field is rapidly evolving with several exciting directions. 3D bioprinting uses shear thinning inks that flow during extrusion but quickly solidify. Understanding these rheologies is critical for printing complex tissue structures. Smart fluids whose rheology can be tuned with electric or magnetic fields open new possibilities for active control of microfluidic processes. Machine learning is being applied to predict rheological properties from molecular structure and to optimize device designs. Finally, integrating non-Newtonian flows with organs on chips creates more physiologically relevant models for drug testing, since most body fluids are non-Newtonian. Non-Newtonian fluid mechanics in microchannels is a beautiful example of how fundamental physics leads to practical applications. The interplay between shear thinning and viscoelasticity creates rich phenomena that we can exploit for advanced microfluidic technologies.